The universe may not be infinite, not in size, and not in how much information it can truly contain. I know how that sounds. We're used to the idea that space is an endless stage. Keep traveling, keep counting, keep zooming in, and there's always more. Infinity feels like the default setting. But there's a reason some theoretical physicists, people like Leonard Susskind, Stephen Hawking, Jacob Bekenstein, and Juan Maldacena keep circling back to a very different possibility. That reality might come with a built-in limit. And the strange part is where the clue shows up. Not in the farthest galaxies, not in the earliest moments after the Big Bang, but at the edge of something that looks, at first, like the ultimate infinite sink, a black hole. So here's the open question we're going to keep pulling on. If the universe isn't infinite, where would that finiteness be written? In the middle of space, or on boundaries we can't touch? Hold that thought. Because first, we need to be precise about what we mean by not infinite. When we say the universe is infinite, we often mix together at least three different claims. One, the observable universe is finite or infinite. That one is easy. The observable universe is finite because light has only had about 13.8 billion years to travel, and the expansion history sets a horizon beyond which we simply can't see. That's not controversial. 2. The entire universe, everything that exists, including regions forever outside our view, is infinite or finite. That is unknown. Observations tell us space is very close to flat on large scales, but close to flat doesn't settle the question of whether space is infinite. And 3, the deepest, most slippery claim of all the one we almost never say out loud. That reality has infinite detail, infinite resolution, infinite information, that you can keep subdividing space into smaller and smaller pieces, and nature will always have room for more independent facts. This video is mainly about that third claim. When I say the universe may not be infinite, I don't mean there's a cosmic wall you can fly into. I don't mean there's an edge with a sign that says END. I mean something more subtle. There may be a maximum amount of information that can be physically stored in a region of space. And if that's true, then the infinity we casually assign to the universe might be a feature of our mathematical description, not a feature of nature itself. To make that feel less abstract, let's start with something familiar. Temperature. Temperature feels fundamental. Hot and cold feel like basic properties of the world. But if you zoom in far enough, temperature isn't a fundamental ingredient. It's a summary. It's a statistical description of countless microscopic motions. The concept is real, extremely real, but it emerges from deeper rules. Pause for a second and picture a cup of coffee. If we freeze time and zoom in, we don't find heat stuff. We find molecules jostling, colliding, trading energy. Temperature is what the system looks like when you stop tracking every micro detail and start using a higher level language. Or consider your phone. On the screen, you see a battery icon. That icon is real in the only way that matters. It reliably guides your decisions. But it's not the fundamental truth of the phone. Underneath, there are chemical gradients, charge carriers, control circuits layers you never see. Now here's the key idea we'll keep returning to. Emergent does not mean fake. Emergent means not fundamental, but still real at the level where it applies. And that brings us to spacetime itself. We tend to think of space as the ultimate territory, the base layer beneath everything else. But modern physics keeps hinting that spacetime might behave more like temperature or more like the battery icon than like an unbreakable stage. Which matters, because infinity is usually something we assign to the stage, infinite space, infinite points, infinite resolution. But if the stage is emergent, then maybe the infinity is too. Now we can climb the ladder slowly through the physics that makes this idea more than a metaphor. Step 1 is the clash between classical and quantum intuition. In classical physics, you can pack information arbitrarily tightly. Take a region of space. Write smaller and smaller. Store more and more bits. If you want twice the information, you shrink your ink. There's no fundamental limit, only practical ones. Quantum physics disagrees. In quantum theory, pushing detail to smaller scales costs energy. If you try to localize something too sharply, uncertainty demands higher momentum. Higher momentum means higher energy. The smaller you try to make your pixels of reality, the more energetic your probe becomes. And gravity notices energy. This is the moment where two theories that feel separate, quantum mechanics and gravity, suddenly cooperate to ruin the dream of infinite storage. Because if you concentrate enough energy into a small enough region, you don't just get finer detail. You get collapse. You get a black hole. Pattern interrupt. Imagine trying to build the ultimate hard drive. You want to store more and more information in a smaller and smaller volume. You're compressing reality itself. At first it works. Then the device gets heavier, hotter, more gravitationally intense. And at some point, the best storage container you can create is no longer a box. It's an event horizon. Already that should make us suspicious of naive infinity. Because infinite information in a finite region starts to look physically impossible, not just technologically difficult. Now we reach the second step on the ladder, black holes and information. For decades, black holes have been the sharpest testing ground for our ideas about reality. They combine extreme gravity with quantum effects in a way that forces contradictions into the open. In the 1970s, Stephen Hawking showed that black holes aren't perfectly black. Quantum effects imply they emit radiation, what we now call Hawking radiation, and over long time scales they can evaporate. Here's the tension. Hawking radiation looks thermal. And thermal radiation by itself seems to carry very little detailed information about what created it. If a black hole forms from a complicated object, say, a library or a planet, then evaporates into what looks like featureless heat, it begins to look like information was destroyed. But quantum mechanics is built on the idea that information is not destroyed by time evolution. The equations of quantum theory, as we normally understand them, preserve information. So which principle gives? This is the black hole information problem. Now, we need to be careful and honest about the status here. What's well established is that black holes have temperature-like properties in semi-classical calculations, and that horizons behave thermodynamically in a deep way. What's widely believed, almost the default working assumption in modern theory, is that quantum mechanics wins. Information is not fundamentally destroyed. Many lines of evidence point that direction, though the full story is still being refined. And what remains actively researched is how, exactly, the information is encoded and how it can, in principle, be recovered. But regardless of the final mechanism, the mere existence of this paradox pushed physicists to ask a new kind of question. How much information can a black hole hold? That question leads to the third step, entropy and the area law. In thermodynamics, entropy measures the number of microscopic configurations consistent with a macroscopic description. In modern physics, entropy is also intimately tied to information. It's a way of counting how many distinct internal states a system could be in. Jacob Bekenstein proposed that black holes should have entropy. Hawking's work then nailed down the idea. Black holes behave like objects with a temperature and an entropy. And then came one of the strangest scaling laws in all of physics. A black hole's entropy is proportional to the area of its event horizon, not the volume inside. Let that land. If you take a normal object, you expect that how much you can store scales with volume. Bigger box, more storage, triple the radius. Volume grows quickly. But black holes say, the maximum information you can cram into a region grows like the boundary area. Not what's inside, the surface. Pattern interrupt. Picture two spheres. One is filled with stuff. The other is just a glowing shell. Your intuition says the full sphere should hold more. Black holes say the shell sets the ultimate limit. This isn't a minor technical detail. It's a signpost. It suggests that the fundamental bookkeeping of reality is not done by counting points in a volume. It's done by counting something like bits per unit area on a boundary. This idea is closely related to what's often called the Bekenstein bound, a bound on the maximum entropy or information that can be contained in a given region, given constraints like energy and size. Black holes appear to saturate that bound. They're not just weird objects, they're the extremal case. And that brings us to the fourth step, the holographic principle. The holographic principle is the idea that the physics inside a region can be fully described by degrees of freedom living on the boundary of that region. When people hear holographic, they sometimes imagine a literal projection, like the universe is a fake 3D image cast from a 2D surface. That's not what's being claimed. When we say holographic, we don't mean the world is an illusion or a simulation in the everyday sense. We mean the deepest description may use fewer dimensions, with the extra dimension, the one we experience as depth, emerging as an effective description. Emergent, not fake. Now we can return to an earlier open loop. If finiteness is written anywhere, it might be written on boundaries. So the next question is obvious. Is holography just a poetic interpretation of black hole entropy, or is there a real example where the idea is explicitly true? That takes us to step 5, ADS/CFT. In the late 1990s, Juan Maldacena proposed a remarkable correspondence, now called ADS/CFT, that gives a concrete, mathematically sharp realization of holography. Here's the intuition without equations. Imagine a particular kind of universe with a geometry called anti-de Sitter, space ADS for short. This is not our universe, but it's a consistent theoretical setting. In ADS/CFT, a theory of gravity in the bulk, the interior spacetime, is equivalent to a quantum theory without gravity living on the boundary. Equivalent means the two descriptions contain the same physics, encoded in different languages. The boundary theory, in principle, has enough information to reproduce everything that happens in the bulk. The extra depth is not fundamental in the boundary description. It emerges. This is one of the strongest reasons physicists take holography seriously. It's not just a hand-wavy story. It's a proof of concept that a universe with gravity can be fully described by non-gravitational degrees of freedom on a lower dimensional boundary. Now we need to say the limitation clearly, because it matters for honesty. Our universe does not look like anti-de Sitter space. Observations suggest that on the largest scales, the expansion of the universe is accelerating, consistent with a small positive cosmological constant, more like de Sitter behavior than ADS. So ADS as CFT is not a literal model of our cosmos, but it is a demonstration that the idea space-time emerges from information is not nonsense. It can be true in a full, rigorous theory. And now we can climb toward the title question. Why might the universe not be infinite? Because if spacetime can emerge from a finite set of degrees of freedom on a boundary, then the infinite continuum of space might not be the most fundamental layer. At this point, let's do another pattern interrupt. Take a breath and flip your intuition around. What if space is not the hard drive? What if space is the desktop? A useful, stable interface that organizes information in a way brains like ours can navigate. And what if the real storage, the thing that fundamentally counts, is not the volume of space but the information capacity of boundaries? If that's the case, infinity becomes something we should treat with suspicion, the way we treat infinite smoothness in a fluid. The ocean looks continuous, but at a deep level, it's made of molecules. The continuum was an approximation that worked extremely well until you asked the wrong question. Now step 6. Emergence is a map for space, time, and matter. If holography is pointing in the right direction, then space-time itself may be emergent from more fundamental quantum degrees of freedom, often imagined as patterns of entanglement and correlation. This is an active research area with many competing ideas, so we'll label things carefully. Established, quantum entanglement is real and measurable. Established, black hole thermodynamics ties geometry to entropy in deep ways. Strong evidence in specific models. In ADS as CFT-like settings, geometry is related to boundary quantum structure. Speculative, but motivated, in our universe, space, and maybe even time, could emerge from quantum information-like ingredients in a more general way. Now, if the universe is not infinite, there are two different senses in which that could be true. The first is geometric. Space could have finite total volume. And the second is informational. Even if space is very large or even infinite, any region that can ever influence you might contain only a finite amount of information. Let's talk about the geometric possibility first, because it's surprisingly intuitive. People often think if the universe is flat, it must be infinite. But that's not true. A surface can be locally flat and still be globally finite. The simplest analogy is a video game world with wraparound. Walk straight long enough and you return to where you started. No edge, no wall, yet the total area is finite. In higher dimensions, there are 3D analogs of this idea spaces that can be finite yet unbounded. They can look flat in local measurements while still having a wraparound topology. Our best observations indicate the universe is very close to flat, but very close to flat does not rule out a finite topology that's simply too large for us to detect with current data. So one reason the universe may not be infinite is simply we haven't measured its global shape well enough to know. Finite is still on the table. Now, the second sense-informational finiteness is where the black hole story becomes cosmology, because black holes aren't the only objects with horizons. In an accelerating universe, there can be a cosmic event horizon, a boundary beyond which events can never affect us, because space expands too quickly for their light or any signal to ever reach us. And horizons, in our best theoretical understanding, behave thermodynamically. They come with temperatures and entropies, and the entropy, again, scales with area. So here is the motivated but not fully settled idea. If dark energy is truly a constant, and if our universe approaches a de Sitter-like state in the far future, then the cosmic horizon may have a finite entropy. And a finite entropy suggests a finite number of underlying quantum states available within that horizon. In plain language, the universe, as experienced by any one observer with a horizon, may have a maximum memory capacity, not because of engineering limits, because of fundamental physics. Now, we should be cautious. The nature of dark energy is still not fully understood. Whether the universe tends exactly to de Sitter space is uncertain, and the interpretation of horizon entropy in cosmology is an area of real debate. But even with those caveats, the repeated appearance of area sets the information is a pattern too loud to ignore. It's as if gravity is constantly telling us, stop thinking about infinite volume as infinite content. The boundary matters. And now we can close another loop from earlier. No edge doesn't mean infinite. A cosmic horizon is not a wall. You don't crash into it. It's a boundary of influence, not a physical barrier. It's an edge in the causal sense, not in the mechanical sense, which brings us back to the title, Why the Universe May Not Be Infinite. Because our best attempts to unify quantum mechanics and gravity keep replacing the naive picture of space as an infinitely divisible container with a new picture, space as an emergent, effective description of underlying degrees of freedom whose total count may be finite per horizon area. So what changes if that's true? Let's lay out a few implications carefully with labels. Implication 1. Mostly established. The observable universe is finite, and horizons are real features of our cosmology. Even if the whole universe is infinite, what we can observe and be affected by is bounded. Implication 2. Plausible. The ultimate storage capacity of a region is finite and scales with boundary area. Black holes strongly suggest this, and many approaches to quantum gravity build it in. Implication 3. More speculative. If the number of states accessible within a horizon is truly finite, then over extremely long timescales the universe behaves less like an infinite playground and more like a system with a finite state space. That raises strange questions about recurrence, repetition, and what randomness means in a world where the number of possible configurations is not infinite. Those last questions are fascinating, but they're also where we can most easily fool ourselves. So we'll keep them as questions, not conclusions. Instead, let's zoom out and capture the core idea in one clean chain. Classically, infinity feels natural because the world is described as a smooth continuum. Quantum mechanics says the continuum is not free. Fine detail has a cost. Gravity says, push that cost too far and you make a horizon. Black holes say the maximum information you can pack into a region scales with the area of the horizon, not the volume. Holography says maybe that's not a coincidence. Maybe the fundamental description lives on boundaries. ASSCFT says in at least one consistent theoretical setting that boundary description is fully equivalent to a bulk world with gravity. And Emergence says spacetime can be real and reliable without being fundamental like temperature, like an interface. So, is the universe infinite? We don't know in the simple geometric sense. It could be infinite. It could be finite with a wraparound shape. Observations haven't settled it. But in the deeper sense, does reality contain infinite, independent information? Gravity and quantum theory together keep pushing us toward probably not, at least within any region that can physically matter to an observer. And if that's right, it reframes the word infinite from a statement about the world to a statement about our models. Infinity may still be indispensable in mathematics. It may still be the cleanest way to write down theories that work extremely well at ordinary scales. But the universe itself may be more disciplined than our equations. Not small, not simple, not limited in any human sense. Just not literally infinite in the number of independent facts it can hold. One last time, because it's the philosophical hinge of this whole story. Emergent doesn't mean fake. Space-time can be emergent and still be the arena in which every meaningful human story unfolds. It can be the right language for planets, light, chemistry, biology, and consciousness, while also being a higher-level description of something deeper. So the next time someone says, of course the universe is infinite, it's worth asking, do you mean infinite distance, infinite time, or infinite information? Because black holes, quietly, suggest that the universe may not grant us that last kind of infinity. If you want more long-form, calm, conceptual physics, no equations, just intuition and the big ideas, consider subscribing. And here's a question to leave in the comments. If reality has a maximum information capacity, should we treat infinity as a powerful mathematical tool or as something nature literally contains?